Okay, our last topic that we want to talk about when discussing forces is something called a free body diagram, or as I abbreviate it, an FBD. Remember this acronym, it's going to be your friend for all of high school physics. Now, a free body diagram is pretty simple. A free body diagram includes a sketch of an object, in this case let's make it a box, any forces acting on that object, in terms of vector arrows, and finally the all-important coordinate system. Now what a free body diagram does is it essentially frees a body from its surroundings. So let's say that this originally looked like a box on a table surrounded by some air. You'll notice that when we moved it up to the free body diagram, we removed everything besides the box itself. So we removed the table, we removed the air, and we replaced the presence of these things with forces, meaning that here this arrow is the force of the table pushing up on the box, and these arrows are all the force of the air pressure on the box. Now we won't get too much into pressure, but the point that I want to put out there is that when we remove the environment from an object in a free body diagram, we replace the effects of the environment with forces. So here's another way of putting it. Let's have an airplane. Big surprise. Say the airplane is traveling like this. Terrible airplane. Now if the airplane is traveling forward, it's usually got air all around it, it's got an engine on it, and it's got wings and everything, but we're not going to draw those things. But instead what we're going to do is we're going to replace it by forces. Instead of drawing an engine, we're going to replace the thrust of the engine with a force forward. Instead of drawing a detailed wing of the engine, we're going to replace it with a lift force. And instead of drawing the big mass of the airplane or the weight or anything, we're going to draw a gravity force. And finally, to represent the drag on the airplane, we're going to draw a drag force. So you see, this is a free body diagram of the airplane, of course, with the coordinate system. And you can see that we've got all the forces there on the body. So what is a free body diagram useful for? A free body diagram is useful for summing all the forces and determining the net force on an object. Now the net force is really important. For example, we can look at the net force in the x direction. The net force, which is a sigma f, which for the sum of the forces in the x direction, is equal to drag, which acts in the positive direction, minus thrust, which is in the negative direction. Similarly, the sum of the forces in the y direction is equal to lift in the positive y direction minus gravity. Now, this is important because remember when I said that force was proportional to acceleration, that any force would cause an acceleration? This isn't exactly true. Only a net force will cause an acceleration. And you know this. For example, if you try to push on your car in the parking lot, it's probably not going to move. The reason is because you have a bunch of friction. You have the parking brake on. Even though you're putting a force on the car, it's not accelerating. What you have to do is you have to supply a force on the car that is greater than the car's friction and inertia in order for the car to actually move forward. You need to have a net force in one direction in order for the car to move. So that's why it's really important to draw free body diagrams, is because you need to figure out, do I have a net force, a non-zero net force in one direction, and if I do, it causes an acceleration. Anyways, that's all that we have time for today. What we're going to be doing next is we're going to be taking a look at exactly what the relationship between force and acceleration is, and how we can quantify how an object behaves through its inertia.